Hello everyone, myself Jayalarita, doing in MSc Physics. Here I am going to discuss about the angular momentum in quantum mechanics. In this, we mainly discussing about angular momentum operators and communication relations. First, let us take a short introduction of angular momentum in quantum mechanics. We have energy, position, linear momentum, and we proposed operators each of these. One other quantity that is important in a classical mechanics is angular momentum. Is also important in quantum mechanics, especially for the hydrogen atom. In classical mechanics, anything that is spinning has angular momentum. Here, the sum of points we have to recall. Angular momentum is sometimes described as the rotational analog of linear momentum. And simply we can say angular momentum is a quantity that is useful in describing the rotational state of a physical system. Then let's talk about eigenfunctions. The linear momentum eigenfunctions are functions of position along a specific spatial direction, and angular momentum eigenfunctions are functions of angles by the specific axis or couple of angles. Thus, unlike linear momentum, angular momentum always has discrete eigenvalues. Now, for example, for eigenfunctions in space, this is associated with the fact once we go on an angle in a circle where a particular axis, we have to be back to where we started. In quantum mechanics, the angular momentum is defined by applying a quantization operation to the classical expression. Thus, the angular momentum represented by L equal to R cross P, where R is a position vector and P is the momentum vector. We will have operators corresponding to angular momentum about different orthogonal axes. So we have one for the x-axis, y-axis and z-axis. But the strange thing about them is that they do not commute with one another. In general, these operators do not share eigenfunctions. Let, in contrast to the linear momentum operators, for example, for the different coordinate directions px, py and pz, which do not commute one another. There is, however, another rather useful operators when thinking about angular momentum. That one is called L square, and that does not commute separately with each of these operators Lx, Ly and Lz. The eigenfunctions for Lx, Ly and Lz are individually going to be quite simple. The ones for L square are things called spherical harmonics, and they look much more complicated. However, they can understood relatively simply. These are particularly important because they form the angular shapes of the hydrogen atom. So, these spherical harmonics are the root of all the orbitals in atoms. So, let's look at classical angular momentum first, and we build up towards quantum directions of angular momentum. Here, we showing some x-axis and y-axis. We emerge some particle or object moving along direction as shown by figure, where momentum vector p, position vector r and the angle theta. So, some classical angular momentum of some small object of linear momentum p centered some point that is given by a position vector r relative to origin. Thus, the formula of cross product of the position vector and momentum vector, that is L equal to r cross p. Now, with classical angular momentum L equal to r cross p, we can also write out this for various components, that is Lx equal to ypz minus zpy, Ly equal to zpx minus xpz, and Lz equal to xpy minus ypx. And we can propose a quantum mechanical angular momentum L. Thus, we going to base that on substituting the position and momentum operators, that L equal to r cross p, that's equal to minus ih bar r into delta. And we can similarly write out component operators of Lx, Ly and Lz. Thus, we obtain three operators Lx, Ly and Lz. Lx equal to ypz minus zpy, that equal to minus ih bar of y into dou by dou z minus z into dou by dou y. Similarly for Ly and Lz operators. And each of these operators we could check is omission. Now about commutation relations. So correspondingly is the operator L itself, because it is sum of the three operators Lx Ly minus Ly Lx, that equal to Lx Ly equal to ih bar Lz, and Ly Lz minus Lz Ly, that equal to Ly Lz equal to ih bar Lx. Third one, Lz Lx minus Lx Lz equal to Lz Lx, that equal to ih bar Ly. Now note that these commutators telling us that in fact these operators are not going to be in general sharing some sets of an eigenfunctions, because these operators do not commute. Let these individual commutation relations can be written in more compact form, that is L cross L equal to ih bar L. Now, unlike operators for position and for linear momentum, the different components of these angular momentum operators, as before said, they do not commute with one another. The commutator are not in general zero, and so this is telling us through a particle can have simultaneously a well-defined position in both the x and y direction. A particle cannot in general simultaneously have a well-defined angular momentum component in more than one direction. It's completed. Thank you.